I am really excited to be here to talk about a topic that I personally am quite passionate about, which is taking data as it's being produced and deriving insights from that data in real time to drive business decisions and actions. So let me set the agenda of what we'll cover over the next 45 to 50 minutes. This is a 100-level introductory talk on stream processing, on real-time stream processing, with a focus on business use cases enabled by real-time stream processing. So what we'll do is we'll cover common stream processing architectural patterns. So I'll highlight the architectural pattern, and for each architectural pattern, I will pair that with a few real-world use cases that leverage that pattern. So this is a very pragmatic talk. We'll cover pragmatic patterns and use cases. So let me also talk about what we will not cover. What we'll not cover is we won't be going under the hood and look at how the various stream processing technologies actually work. So we won't look at how they work. We'll look at how to use them for your use cases. We'll also not be looking at snippets of code. We won't go to the code level. We'll stay at the architectural pattern level. The second half of this talk is actually what I suspect will be more compelling to you. We are fortunate to have Syarif Hidayatullah from GO-JEK come here and join us and talk to us about various stream processing use cases, business use cases implemented at GO-JEK. A lot of these use cases have actually been implemented by Syarif, who is a data engineer. So we're very fortunate to have him here talk about these use cases. GO-JEK is a fascinating company. It is a fast-growing company based in Indonesia, and they have a presence in other parts of Southeast Asia as well. They have a bunch of offerings, and I'll let Syarif talk about GO-JEK in more detail, but let me just give you a preview. Most of their noteworthy offerings are in ride-hailing and logistics or delivery. So really excited to have Syarif here talk about how they've implemented business use cases that leverage real-time stream processing. And towards the end, we'll leave a few minutes for Q&A. So before we dive into the architectural patterns, let's take a step back and look at the big building blocks for most end-to-end real-time stream processing applications. So at the very left, we have the sources of data, the applications that are generating the continuous streams of data that we'll be processing. The first thing you want to do is take those streams of data and write them to a reliable, scalable, high-throughput streaming data channel. Think of this as the big pipes through which your streaming data moves. And the two most common options are Apache Kafka, which is a popular open source option, which is available on Google Cloud. And then the other option is PubSub, which is Google's fully managed and serverless offering. Well, after you've ingested the data, often that data is going to be in a raw format, not a format that is amenable for analysis. So you want to take that raw data and transform that data into a format that is much better for analysis. And you do that in real-time stream processing engines. And on Google Cloud, the two most common options, the recommended options, are either Dataproc or Dataflow. So Dataproc is Google's managed offering for the popular open source distributed processing engine, Apache Spark. Dataflow is Google's cloud-native solution for both stream and batch processing, and Dataflow is a fully managed and serverless offering. Well, so after you've transformed the data, now it's ready to be analyzed. You can do the analysis in Dataflow or Dataproc itself. Both offer fairly flexible programmatic SDKs. So you can do arbitrary analysis and processing within Dataflow or Dataproc. But another common pattern is you take the transformed data and you write it into BigQuery. BigQuery is our infinitely scalable, fully managed, SQL-based data warehouse in the cloud. So once the data is written to BigQuery, you can issue SQL queries to BigQuery and analyze the data. So great, at this point, we have analyzed the data and we've likely derived the insight that is of interest. But the whole point of real-time stream processing is to make that insight or the results of our analysis actionable in real time, which means that invariably means there has to be some end-user facing application where the insight or the results of the analysis are served. And to do that, we write the analysis to to systems, to data stores that can serve the data. Common options here are NoSQL stores such as Bigtable and Data Store. Cloud Spanner is a transactional database that is increasingly becoming popular for stream processing use cases. And of course, you can write the data to BigQuery, because when a SQL query is issued to BigQuery, say through the JDBC client, it immediately serves the results. So you need some system to serve the results to the end user applications, and that happens through BigQuery, Bigtable, Data Store, or Spanner. There are other options as well. You can use Cloud SQL and so on and so forth. But in stream processing, these 4 options listed here tend to be the common options. Now, I do want to highlight that on Google Cloud, these tools are seamlessly integrated so that you can focus on your application logic, and the APIs are neatly integrated for you to transfer data from one system to the other, to read data and write data from one system to the other. And the other thing I want to highlight is most of these tools are managed, and some of them are serverless. And what I mean by managed and serverless is a managed offering is one where you as a user do not have to worry about spinning up clusters, managing VMs, and scaling up and down. And serverless offerings are where you can just forget that there's a cluster in the background. You just submit your workload. We take care of spinning up VMs on your behalf, scaling them up and down, and so forth. So it's really compelling, because these are all seamlessly integrated, and many of them are managed and serverless. So with that, let's start and dive into some specific patterns. But first, let me set some context. For simplicity, when I talk about a pattern, I will have an architectural diagram that just focuses on the pattern. And just to keep things consistent, we'll focus on using PubSub as our default streaming data channel, and we'll use Dataflow as our default stream processing tool of choice. I do want to highlight that in real-world use cases, you will actually be combining a bunch of these patterns. But over here, just for simplicity, so when you look at an architectural diagram, it's easy to read. I'll just highlight one pattern at a time. I just want to repeat, real-world use cases will clearly be a combination of these. And when you look at Syarif's talk, that actually become very apparent. And before we move on, just one piece of advice, always archive the raw data. With stream processing, mistakes will happen, and often mistakes happen because of errors in user code. And if you've not archived the data, it can become difficult to recover. But if you've archived the data, then you can always backfill, recover by running a batch job and so forth. So just a rule of thumb, always be safe, archive the raw data. And of course, you don't need to keep the archived data for years on end. Keep it for a few months, and then when you know that things have worked fine, you can discard the archived data. And often, archiving the data has very little cost. All right, so with that, let's dive into the first pattern. And the very first pattern I want to talk about is very simple. It just entails reading the data streams, events that come in, and writing them directly into BigQuery. BigQuery has an API called the BigQuery Streaming API. It's a high-throughput streaming API. And as soon as you write an event into BigQuery through this API, any SQL query issued to BigQuery thereafter will have results that incorporate these new events. So in many cases, to do real-time processing of data, all you have to do is stream the data into BigQuery as it comes in. Of course, that won't always work. This works when your data comes in a JSON format. And often, you want the fields of the records to match the columns of your table. There are non-trivial use cases where that is the case. You have JSON data coming in, it maps to the fields of your table, you just write it in, and you're good to go. And often, real-time stream processing is as simple as that. And I did mention this is a pragmatic talk. I'm not always going to get into sophisticated stream processing, and in many cases, this is all you need, and you're good to go. But of course, that's not going to be true all the time. In most cases, you will need to do some processing of the data because it comes in a raw format. And you want to do some transformations to convert it from whatever raw format it came in to some slightly structured format that is amenable for analysis. In many cases, you will get malformed data, and you want to filter out the malformed data. As you're doing the transformation and cleaning, you might convert data from strings to more structured fields like date time fields and ints and fields and floats and so forth. So you do that in Cloud Dataflow. In Cloud Dataflow, you can take the incoming data and process each event one by one. So over here, we're talking about something fairly simple where you're not looking at multiple events in aggregation. You're actually looking at each event in isolation. And of course, in many cases, the events coming in are not going to have all the information you need to do your analysis. So what you need to do in many cases is join the incoming data with relevant metadata that will be in other data stores. And common data stores that hold metadata might be in some BigQuery table. It could be, BigQuery table. It could be in Bigtable or Spanner or even other relational databases like Cloud SQL. So you join the incoming data with relevant metadata from other data stores. You've enriched your data, and now you have your transformed, clean, filtered, enriched data. You write it into BigQuery, and you're ready for analysis. Now, I do want to highlight that systems like Dataflow, the SDKs provide very easy to use operators. So you merely invoke the operator to do transformations or filtering or joins, and often you actually have to provide just a small snippet of code that contains your custom logic that determines what you want to do with the events. So the SDKs make all of this very easy. And of course, these systems are integrated, so moving data from one place to the other is also incredibly easy thanks to the pre-built APIs. Now, let's talk about business use cases. Now, when it comes to writing data to BigQuery in real time, this is applicable across industries and business use cases. This is applicable in any situation where you're using metrics and dashboards to run your business, which increasingly is most businesses. In many cases, you just stream the data in, and you now are having dashboards. So when you issue a BI query, the results reflect what happened now. They're not reflecting what happened yesterday. And I want to contrast this with what happens traditionally, where you might have a daily job, an ETL job. ETL is the term commonly used. You have an ETL job that's taking your raw data and doing a whole bunch of transformations in a batch format and then loading it into your analytic data warehouse. Now, don't get me wrong, there will still be use cases where you need to do that batch processing because whatever analysis you're doing in that job may not be amenable for a streaming pattern. But if you look at your ETL jobs, you'll find that a significant chunk of those jobs can be converted to streaming jobs. And if you convert them to a streaming job, dashboards that are powered by that data reflect the state of the world as of now, not as of yesterday or as of last week. Very cool. So now let's look at a slightly more sophisticated pattern where you're actually looking at a whole bunch of events together. In many scenarios, what you're interested, particularly when you're talking about real-time analysis, what you're interested in is what happened in a very recent or the most recent window of time. What you're interested in knowing is what happened in the most recent 30 seconds or the most recent, say, 5 minutes, or maybe even a couple hours. But the key thing is you want to know what happened in a recent window of time. And as time proceeds, you want to constantly look and analyze what happened within the most recent window. And to do that, you used fixed or sliding windows. There's a subtle difference between the two. Fixed windows don't overlap. So one window ends and the next window begins. And then with sliding windows, you actually have a large window that moves a little bit every time. So there is overlap across subsequent windows. And depending on your use case, you can use one or the other. Essentially, you pick the type of window you want. You invoke the window within your code, and you provide another snippet of code that determines how you want to process the events that fit into a particular window. And then the framework essentially handles the rest. The framework will handle the creation of these windows and the collection of the events that fit into a window, and essentially it'll keep track of time, and as soon as a window completes, it'll call your snippet of code to analyze the events that fell into that window. So the framework simplifies this windowing process significantly. So now let's look at use cases that are enabled by this, and there are a whole bunch of use cases. Let me start with retail and e-commerce because they often tend to be use cases that are easy to understand and empathize with. So with e-commerce, let's say you want to keep track of popular items. You want to know items that are becoming popular as soon as that trend starts to surface. And you may not really care about the popularity of that item last week or yesterday because you want to catch trends early. So what you do is you keep track of the searches that people are issuing in the e-commerce website, and you're analyzing the searches that came in within, say, the past couple of hours, and then you know the products that are popular now, and then you can match that with your inventory to know if, let's just say, the inventory cannot keep up with the demand, or if demand is higher than the inventory, then you can do dynamic pricing. Similar use cases where you might have some product quality issues. A new batch of products came in and they have some defects, so now you're seeing a high number of complaints or returns. And you want to capture that very quickly. And when you're capturing this, you're not really interested in the number of returns or complaints that came in last week. You want to know what happened in the past, say, few hours. And again, fixed and sliding windows enable that. There's similar use cases in IT operations when you're tracking metrics, and you can see how that metric is moving over a recent window of time, and you can also contrast that with the historical information. It's also particularly common in finance, where for stock trading strategies, a lot of their strategies actually look at multiple windows of time simultaneously because they want to know how the stock is moving. So a bunch of use cases that leverage fixed and sliding windows. Now actually one more use case before we move on. There are certain use cases where you're not necessarily interested in what happened in the most recent window. What you want to do is you actually want to do some smoothing and denoising. And this is particularly true in IoT, where you have a lot of cheap sensors, and these sensors are sending information, but the information coming in is often very noisy. There's a whole bunch of noise, and you don't want to be making big decisions based on the value of one sensor reading. So an easy way to deal with that is you define a reasonable window of time, and you just average out, say, the sensor values within that window. So that essentially serves as a simple denoising and smoothing technique, which is common in IoT use cases, and it's also applied in similar other use cases. Very cool. So moving on, now let's talk about a fairly distinct but very popular type of windowing called session windowing. And this is useful for consumer internet and mobile applications. Essentially, what session windows are used for is collecting your click logs, all the activity that users perform on the web application or the mobile application, all that information is streaming in, and what you want to do is isolate each user's session so you can analyze what happened within that session. So this is different from fixed and sliding windows because the windows are not fixed, and also you have a separate window per user. So all you have to do is, in the framework, you just have to mention what is the field in your incoming events that corresponds to the user ID, and then the framework will automatically split the events based on that user ID. And then you have to pass another parameter, which is the duration of inactivity that signifies the end of a session. Because there are many ways a session has ended. The most common way tends to be, okay, the person is no longer active on my application, so let's consider the session to be done. So you specify these two parameters. What is the key that specifies the user ID? And what is that duration of inactivity that signifies the end of a session? And the framework handles the rest. The framework will take these events, split these events by ID, determine when a window has ended, and as soon as that window has ended, it will invoke your snippet of code. And no surprises here. This is used by consumer internet and mobile applications to understand how users are navigating through that application. Because what you are able to do is get the events that fell within a session, so you can actually understand the fact that the user came in, may have issued a search query, then clicked on a certain button, stayed on a certain page for a certain duration of time, and so on and so forth. So you analyze each session, write the results to BigQuery, and now you actually have an aggregated view of how users navigated through your application. And this is a very common use case, particularly when you are deploying new versions of your application or you're doing A/B testing. You want to identify mistakes soon. You want to identify something you might have shipped that is leading to a significant drop in a certain usage pattern that is critical. So as soon as you run your A/B test, you have your streaming job analyzing user sessions, identify issues quickly, and maybe roll back. It's a very common use case and a fairly distinct use case that was worth calling out. So that was windowing. So moving along, now let's talk about a topic that is likely to be popular, GCP and Google Cloud Next. Machine learning is clearly a theme of the conference. And in many scenarios, you want to apply machine learning within a streaming context. Actually, quick show of hands. I'm curious to know how many folks in the audience are interested in applying machine learning on streaming data. All right, that's as I suspected. There's a lot of interest. Now, in this particular scenario, I'm talking about users training their own custom models for their use case. And that training, that heavy lifting happens in a batch format, and it happens not within the streaming engine. It'll happen in something like Cloud Machine Learning, CMLE, which is Cloud Machine Learning Engine that lets you train your own models. In this particular diagram, I'm using TensorFlow because that was the most recognizable logo that I could use to signify machine learning. But of course, you can train other models, scikit-learn, XGBoost, or a bunch of other frameworks that let you do machine learning. Of course, the heavy lifting is happening where you're training a machine learning model. But once it's trained, you can leverage that trained model within your streaming application to do inference or scoring on the events as they stream in. Now, of course, before you can do the scoring, and I want to reiterate the fact here that a real-world use case will employ a bunch of other streaming other patterns that we mentioned. Often before you can pass the data to the machine learning model, you'll be doing a whole bunch of transformations. Joining and enriching the data from external metastores is very common because you want to fetch features. You do the transformation, create the feature vector, pass it to the model for scoring. Now, some of you may be thinking that this doesn't sound very remarkable because it's rather simple to take a machine learning model and invoke it within the context of a streaming application. And that is true. This, as an architectural pattern, is not tremendously remarkable, but I wanted to reaffirm the fact that this is happening. This is a very common pattern. And it's actually a very easy to implement pattern. And often within your streaming application, you can constantly be checking to see if a new model has been produced. And when a new model is produced, you take the new model. Or often customers even run some A/B testing where they're using a bunch of models to score different events and see what's happening. I just wanted to reaffirm that this is a very easy pattern to implement with GCP tools, particularly when you're using something like Cloud Machine Learning Engine and customers are doing it. Increasingly common pattern, and a lot more customers are doing it. So let's look at a few use cases. E-commerce and finance, real-time fraud detection. That's sort of the poster child for real-time stream processing and machine learning. So I actually won't beat that horse anymore. I'll move on. There are other use cases, for example, digital advertising, where you have all the click and impression information streaming in all the time, and you can use that in real time to determine what ads have the highest proclivity of being clicked. So as the data streams in, you apply a machine learning model, and you can determine what is the right ad to show for subsequent users that come in. Now, these are all, again, fairly, I guess, relatively known use cases, because digital advertising has been around for a while. I'm particularly, it's gratifying to talk about use cases in healthcare, where literally lives are being saved. A very commonly referenced use case is one of doing sepsis identification. Sepsis is a condition that happens after fairly invasive operations. It's a type of infection, and historically, nurses would have to keep checking in on the patient periodically to see how they're doing, to see if they're at risk for sepsis. But now, because patients are connected to various devices and you're monitoring their vital statistics, as that data streams in, you can apply a machine learning model that can determine who's at risk for sepsis. And if a patient is identified, a pager alert can go out to a nurse. So the nurses don't have to proactively keep checking, and you can offer more proactive care to the post-operative patients. It's a particularly gratifying use case to talk about. Now, in the previous example, the user had to build a machine learning model, but that's not always true. Again, if you've, at Next, you might have visited a bunch of talks where we spoke about our machine learning APIs that do the machine learning for you. You give us the data, the images, or the speech, and so forth, and we apply the machine learning and return the results. And invoking these APIs from a streaming application is, again, an increasingly common pattern. And again, it may seem unremarkable because, again, the heavy lifting is happening in the machine learning APIs. That is actually true. This is, come to think of it, a fairly easy pattern to implement, but it's an increasingly common pattern. And just one piece of advice, when you're calling these APIs, you want to, for proper performance, you want to limit the amount of data that's going over the network. So commonly what people will do is they'll use a fixed window or even a sliding window, but often a fixed window, so just to kind of group a few events and then make batch calls to the APIs, or rather make calls to the APIs with a batch of data rather than calling the API each individual time. But again, this is a very simple pattern, but it enables some fairly compelling use cases. And let me walk through these. There's one use case, and these are actually use cases that customers have implemented. There's one use case where if you have multiplayer online sessions, this is where a bunch of folks are wearing their headsets and microphones and they're playing, say, a first-person shooter or World of Warcraft or what have you. They're constantly talking to each other and they're playing against each other. Sometimes these sessions actually turn verbally abusive. This is a common problem, and now with The speech-to-text APIs, as that speech information comes in, you invoke the API, you convert that speech to text, and then you convert that text, you apply NLP techniques to identify when it's becoming abusive, and then you can take corrective action in that session. Another use case is finance, where for trading strategies, you want to consume the world's text news information about the various organizations of the world. Thomson Reuters, for example, serves a whole bunch of financial news. You want to consume that news information, invoke NLP APIs to identify the entities mentioned in the news articles, and also the sentiment of the news article, and that is a rich source of information to determine trading strategies. Another example, which is, I guess, a du jour example in today's world is for home security, where you have your camera feeds, security camera feeds coming in, and you can invoke vision APIs to identify entities in the image frames, and you can use that to dynamically determine when there might be a physical threat outside that security camera, so outside your home and so forth. So very cool, simple pattern, but very useful pattern. Now the last pattern I want to talk about is a slightly more sophisticated pattern than the other ones we've discussed so far. It's called stateful streaming, and this is a pattern where as the events flow by, you're maintaining some state information about the entities in your events, and you're using that state information to take some business decision. Again, the key thing here is the framework really simplifies this. It gives you APIs where based on a key, such as a user ID, you can add state information, and that information is kept in memory. You can add state information, you can read the state information and take action, or you can update that state information. So you as a user often just have to write snippets of code to do the add, read, lookup, and update operations. And then the framework handles the rest. The framework will make sure that the state information, and it can be arbitrary information, it's up to the application to decide what is maintained. The framework will make sure that this information is maintained in memory and is available in a performant fashion. So, and these are often distributed applications, so it'll make sure that fault tolerance is covered, that if a VM goes down, for example, the state information isn't lost. The framework will take care of that. So you as a user just have to focus on your lookup, update operations often. So let me just talk about one use case where this is used. The use case is e-commerce, where you have click events and events that tell you about the activity of the user on the e-commerce website. As these events come by, you can keep information. The user, for example, searched for these products. The user added a certain product to their cart, removed a certain product for the cart, and so on and so forth. And based on that information, as the next event comes in, you can dynamically determine how to personalize the experience of the user. So you can dynamically determine, for example, that, hey, the user removed an item from the cart, but is still searching for similar items. Let me give them an offer. Or let me dynamically adjust the recommendations that are made for similar products and so forth. So that's what stateful stream processing enables, and there are other use cases as well. For example, we have a customer where in mobile gaming, they're dynamically customizing the difficulty level of the mobile application when they identify that a user is getting stuck. So a whole bunch of streaming patterns, and we did a whirlwind tour of common patterns. And next, please join me in welcoming Syarif to stage and talk about GO-JEK and how they're using real-time stream processing. Thank you.
So good afternoon, everyone. So I'm Syarif from GO-JEK. I'm data engineer from GO-JEK in the BI. And today I want to share with you about the real-world examples of GO-JEK using data flow as our data streaming and batch pipeline. So GO-JEK is an Indonesian-owned technology startup that has specialized in transport, food delivery, and payments. And GO-JEK started in 2010 with only call center. With no application, we created GO-JEK services. So GO-JEK is like ride-hailing service motorcycle in Indonesia. And in 2015, GO-JEK launched an app with only 3 services. We have GoMart, we have GoFood, and GoRide itself. And in 2016, GO-JEK had expansion in 50 big cities in Indonesia and created new services since. And this is our application, our service by now. We have currently 18 products serving very different needs. And this is GO-JEK footprints nationwide. Currently, we have 1 million drivers, which completed 3 million trips per day. And our application already downloaded more than 76 million downloads, and we have more than 200,000 merchants in 50 big cities in Indonesia. And we move to our GO-JEK data growth. So in BI, this is our current state in second quarter of 2018. From the previous month until this month, our data growing more than 30% per month, and from that data, we can create more than 700 multi-resolution data sets. And from that, we can create more than 20,000 data points. From our data analysts, they create the metabase and Tableau sheets. And from there, they create more than 13,000 metabase cards and Tableau sheets. And our user, which means our analyst, created, the user is more than 2,000 at that moment. And this number are increasing day by day. It means we need more big platform and more scale for that. So what is the challenge from the previous architecture we have? Previously, we used PostgreSQL, Pentaho, and also the Python script. And the previous architecture, we have a report at the day +1, so we couldn't identify the problems at the moment. And we already also had a concern about the processing power because data comes in batch and it's already big. So we need to process over 2 billion data in one shot because it's big. So we need a bigger machine with bigger RAM, a bigger CPU, and takes a long time to process the data. And the business needs more real-time data insights. So previously we used PostgreSQL. As you may know that PostgreSQL needs maintenance daily, weekly, monthly. At least you have to archive your data, you have to vacuum your data, and you have to reindex your data to remain your query fast. And you also need to maintaining the Postgres server itself. And we also use the Pentaho and Python script to do our ETL batch, which comment by the Airflow. Then what's next? We move to our GCP platform. And what we want is, we want high performance scalability with minimal operational maintenance using data flow, with more granular data with high velocity, and less latency using stream processing. And we want to be able to solve business problems with real-time data insights. So at the moment, we use Driver to monitor all log, jobs, and the machine. And we use GCS for our data lake. We use BigQuery as our analytical purpose database. We use PubSub to deliver our streaming message. And we use Dataflow for our streaming data pipeline. So we move to the use case. Before we move to the use case, I want to show you about the GO-JEK goals. So what is GO-JEK goals? The GO-JEK goals is on the North Star metric. So what is North Star metric? North Star metric is something that you want to align with the organization behind, so the entire company knows what company goal is. So at GO-JEK, that will be complete booking transactions. So what is metrics that matter when we want to increase the completed booking transactions? We have also to increase the total bookings. We have also need to consider about the allocation and reduce the cancellation rate. Total bookings is the bookings that created by the customer, and the allocation is something that we want to align about the customer and the driver, and the cancellation rate is the when the customer created the booking, the driver couldn't complete it. And for that use case, I want to show you that when the allocation is mismatched between the driver and the customer, the complete bookings wouldn't be reached. So how to rebalance supply and demand? And how do we view it in real time? So this is the GO-JEK supply demand use case. So as a user, I want to know which location have mismatched levels of supply demand in real time. And I want to know the particular drivers are based on the real-time data aggregation. So if you see the map in front of you, if I hover our pointer in the small dots, which is the driver, I can know the driver detail information according to the name, the plate number, and also the rating of the driver itself. And I want to able to notify driver in low demand area to move to high demand area. So this is, after discussion, this is the pipeline we already made. And as you know, we have so many pipelines here. We have 3 big pipelines in here. Well, the one is streaming booking count pipeline. The second one is dimension pipeline from the BigQuery. And stream driver location pipeline we got from the PubSub driver location log or the driver ping. For your information, our driver ping is created by every 10 seconds. It means, and that day we have more than 10 billion data pings. So from the streaming booking pipeline, we consume from our PubSub booking log or messages, and we created a model which grouped by the S2 ID and also the status, and we used sliding window. As Anand mentioned before, the sliding window, we only concerned about the current window, and we filter with only created status. And the dimension pipeline, we query from BigQuery, we go from 3 tables, location table, service alley table, and also the driver profile. Each of them will create each model and will be refreshed or windowed per day. And on stream driver location pipeline, we consume from PubSub driver location log, and we created a model, and we use fixed window. And after that, all of them will be joined and will be stored to our strong stream log memory store, and our API will call the stream log memory store, and we'll create the mapping from this. And we move to implementation. For the implementation, we only focus about how we code. So we just code the data, we just code the pipeline using the Apache Beam SDK, and we deploy it to the data flow, and that's it. We didn't spin up any machine, any cluster, or stack driver. What we have to do is just push the code to the Apache Beam, and Apache Beam will do the rest, like creating the machine and create the pipeline view for us, and also the stack driver by default. And this is the pipeline implementations that already happened. As you can see, this is the auto-scale capability of data flow, which means we can, data flow can scale from 1 worker to several workers based on how big your data and how big your processing is. And this is the scatter implementations. It's fast forwarded. Actually, it's refreshed in every minute. Okay. So the idea of the insight in here, we got that the red circle don't last long, which is good because the booking might be big in those areas, but not for a long time because the driver took the order immediately. So the aggregated booking, the credited, will be disappear after several minutes. But that insight is not enough. How if in that particular area there also canceled booking happen in that day? So if there are many booking, it can be completed or canceled. How can we make sure that every booking is completed, not canceled? So that's why we created extended use cases. And this is our extended use cases to cancellation alert use case. Previously, we got this chart at the day after, at day +1, and we could say that, oh, there's something happened yesterday. There's a spike of cancellation yesterday. But why was that happen? But that was too late because that was yesterday, and maybe today it not happened. So as a user, I want to be notified when there's huge cancellation at that time, so I can determine the root cause and fix it as soon as possible. You know this pipeline before, this from our main use case. From this use case, I want to show you that in Apache Beam, we can create a fan out from this previous pipeline, so we don't create pipeline from scratch. What we have to do is we have to concern about the stream booking count pipeline only, because we don't care about the dimension pipeline and the stream driver location pipeline, so we move it out. And after we created the model, which is grouped by booking status and S2 ID, we create a find out to sync to PubSub downstream and will be consumed by our cancellation pipeline. And the result will be like this. This is our stack driver. As you may see, for example, if the threshold of cancel booking is more than 10% of total booking, it will give the alert And after it go up the threshold, it will give us the alert like this. The alert cancel booking is more than 10%. But again, that's not enough. How do we know the reason? After we get the alert, so what? I couldn't do anything about it. We have to know the reason behind the canceled booking. And this is another use case again. So as a user, I want to know the reason cancel booking in real time, and I want to notify myself and the merchant if item may be sold out, or maybe the price difference with the apps and the current store, or maybe store is closed out of the scheduled. And this is the new pipeline that we created. We still consume from our PubSub booking log. We filter status by the canceled only, and we create the different model. We created by group by the S2 ID and the canceled reason, and we use fixed window, and then we sync to our PubSub downstream, and we created notification system, and also this pipeline can be synced to our BigQuery, so our analysts can determine the result better. So this is the JSON format that we sync to the PubSub downstream. It includes the S2 ID, and the merchant name, and also cancel reason, and how many it happened in that day. So after the use cases, 3 use cases, I want to share with you about the 3 takeaways that our lesson learned about using data flow. With data flow, we can create the streaming data processing. We are able to solve business problem with real-time data insights. And data flow delivers high-performance scalability with minimal operational maintenance. As you already get that, data flow can scale from 1 to several workers based on how big your data and how complex your processing is. And our report will be delivered less than a day, so our analysts can do more, getting more insight with more recent data. And that's all for me. I will back to you, Anand. Thank you very much.
Thank you, Syarif. Please do stay on stage. So it's always useful and quite fascinating to hear about real implementations from customers. And I guess one thing I want to highlight, which was particularly fascinating, was the fact that they built one complex use case, and then they found out, oh, guess what? I can take what I've implemented and with small tweaks convert it into a new use case. So that was quite fascinating. And the tools on GCP do enable that easily. So if you want to learn more, please point your browsers to this URL. So essentially, cloud.google.com, solutions under the big data category, streaming analytics. And from that website, it has links to other deeper information that you might want to, that you want to get access to. So please do direct your browsers to that website. And with that, thank you for listening to our talk. We hope it was useful for you.